Welcome to this Masterclass Explainer. Today, we're diving deep into the fascinating organic chemistry of alcohols, phenols, and ethers. If you've ever wanted a really clear, structured breakdown of this essential syllabus topic, well, you are in exactly the right place. Let's get started.
So right off the bat, can you imagine a world without paper, beautiful photographs, or even polished wooden furniture? It sounds crazy, but without the hydroxyl group, everyday items like the paper we write on, cotton fabrics, and even the spirit used for wood polish simply wouldn't exist. These molecules literally build our modern world, so understanding how they work is absolutely crucial. All right, here is our syllabus roadmap for today. First, we'll meet the hydroxyl family. Then, we'll cover methods of preparation, physical properties, acidity and reactions, important named reactions, and finally, ethers, synthesis and cleavage. Let's jump right into Section 1, Meet the Hydroxyl Family, where we'll look at classification and IUPAC naming. We actually categorize these molecules based on exactly where their hydroxyl, the OH group, is attached. For alcohols, they're classified by their attachment to an sp3 hybridized carbon of an alkyl group. Depending on how many other carbon groups are attached to that specific spot, we get primary, secondary, or tertiary alcohols. But contrast that with phenols. In phenols, that OH group is attached directly to an sp2 hybridized carbon of an aromatic benzene ring. And let me tell you, that direct aromatic attachment completely changes their chemical behavior, as we're going to see very soon. Now, IUPAC rules provide our standardized language here. The basic rule for alcohols is super simple. You just drop the E from the parent alkane and add the suffix -ol, using numbers to pinpoint the position. So the common name isopropyl alcohol, that translates to propan-2-ol. And notice how polyhydric alcohols, the ones with multiple OH groups, are named. Ethylene glycol translates to ethane-1,2-diol, where we actually keep the E of the alkane and use the prefix di. This structured naming basically tells you exactly how the molecule is built, like a blueprint. Moving on to Section 2, Methods of Preparation, or as I like to think of it, giving birth to molecules. First step is hydroboration oxidation, and it's this brilliant multi-step mechanism. Diborane first reacts with an alkene to form trialkyl borenes. Then, we use hydrogen peroxide in an aqueous sodium hydroxide solution to oxidize it. The really crucial takeaway here is that this specific reaction yields an alcohol as if water was added in a way completely opposite to Markovnikov's rule. The boron atom attaches to the sp2 carbon with the greater number of hydrogen atoms, which gives us an excellent yield of our targeted alcohol. Now, if you want something incredibly versatile, you have to look at preparation from carbonyl compounds using Grignard reagents. By just choosing your starting compound, you can precisely control what type of alcohol you build. React a Grignard reagent with methanol, and boom, you construct a primary alcohol. Use other aldehydes, and you build a secondary alcohol. React it with a ketone, you get a tertiary alcohol. It's essentially a customizable chemical toolkit right at your fingertips. All right, let's hit Section 3, Physical Properties, or what I call the personality of molecules. When we compare compounds that have very similar masses, the differences in boiling points are actually pretty dramatic. Take the alkane and pentane, it's hovering at 309.1 Kelvin. Its ether cousin, ethoxyethane, is slightly lower at 307.6. But then, look at the alcohol, butan-1-ol. It absolutely skyrockets up to 390 Kelvin. So what's going on here? Why does this specific alcohol require so much more energy to boil compared to the others? Well, the secret behind those massive boiling point spikes is intermolecular hydrogen bonding. Because of the polar nature of the OH bond, the positively charged hydrogen atom of one alcohol molecule is strongly attracted to the negatively charged oxygen of a neighboring molecule. It acts exactly like molecular glue, creating this sticky, interconnected network. To boil the alcohol, you literally have to supply a ton of extra energy just to break that network apart. Section 4, Acidity and Reactions, the Molecular Tug-of-War. So both alcohols and phenols can act as Bronsted acids, meaning they can donate a proton to a stronger base. But there's a catch. Ethanol is just a weak Bronsted acid. Phenol, on the other hand, is 1,000,000 times more acidic than ethanol. 1,000,000 times. And this massive difference all comes down to the aromatic ring. When phenol donates a proton, it becomes a phenoxide ion. I want you to think of the benzene ring as the center of a chemical tug-of-war. If you attach electron withdrawing groups, like nitro groups, to the ring, they pull electron density away.
This actually stabilizes the negatively charged phenoxide ion and massively boosts the acid strength. Conversely, if you have electron-releasing groups pushing charge into the ring, that destabilizes the ion and decreases acidity. It's all about that push and pull.
Now, we can use chemical reactivity to physically identify molecules in the lab, and we do this using the Lucas test. We take Lucas reagent, which is concentrated HCl and zinc chloride, to see how fast an alcohol forms an insoluble alkyl halide, creating a cloudy, turbid solution. Think of it like a stopwatch. Tertiary alcohols form halides so easily they turn turbid instantly, at 0 seconds. Secondary alcohols take about 5 minutes, and primary alcohols, they produce 0 turbidity at room temperature.
Moving on to Section 5, the VIPs of phenol chemistry, important named reactions.
There are 2 critically important ones you really need to commit to memory: the Reimer-Tiemann and Kolbe's reactions. The Reimer-Tiemann reaction is an electrophilic substitution that brilliantly transforms phenol into salicylaldehyde. Kolbe's reaction, meanwhile, leverages the fact that in an alkaline medium, like sodium hydroxide, phenol generates a phenoxide ion. This ion is even more reactive than phenol itself towards electrophilic aromatic substitution, which is what drives Kolbe's reaction forward.
And finally, Section 6, ethers, synthesis and cleavage. Let's talk about the alkoxy hydrocarbons.
Ethers are beautifully simple to classify based on their structure. They are symmetrical if the groups attached to the central oxygen are identical, like having 2 ethyl groups in diethyl ether. If the attached groups are different, say an ethyl on one side and a methyl on the other, it's an unsymmetrical or mixed ether.
The crucial point for ethers is really understanding their overall chemical profile. They are famously prepared via Williamson synthesis or by the careful catalytic dehydration of alcohols. And I do mean careful. This dehydration mechanism requires highly specific temperature controls to ensure we actually get an ether instead of an alkene. Now, because they don't have a hydrogen directly attached to their oxygen, they cannot form intermolecular hydrogen bonds with each other. That's exactly why their boiling points drop back down to resemble alkanes. But they aren't totally inert. Their carbon-oxygen bond can be cleaved by strong hydrogen halides. But wait, here is a brilliantly tricky question for you. We just established that ethers lack that OH group, right? They can't hydrogen bond with themselves. So why do ethers, like ethoxyethane, still dissolve in water to almost the exact same extent as their alcohol counterparts like butanol? Well, it's because that lonely oxygen atom in the ether can still reach out. While ethers can't hydrogen bond with each other, their polar oxygen can act as an acceptor. It forms strong hydrogen bonds with the hydrogen atoms of the surrounding water molecules. That molecular handshake is what allows them to mix so readily with water. And that brings us to the end of our roadmap. From the early days of isolating phenol from coal tar to the modern creation of detergents, antiseptics, and literally the pages of our notebooks, these molecular families build our modern world. As we continue to master these reactions, it really leaves us to wonder, what will synthetic chemistry unlock for us next? Keep that curiosity alive, and thanks so much for joining me in this explainer.